So 333, zeros and multiplicity. So I'm going to skip examples 1 and 2 because I need division before I can do examples 1 and 2. So just humor me. We're going to move on to example 3. So it says graph example 3. Using a graphing calculator, sketch the graph and find all roots, which is a 0, right? All x-intercepts. And then use the roots to write the polynomial in factored form. So I can do it for you, or you could graph it on your own calculator. 2x to the third plus 5x squared. Go. So I'm putting this in my graphing calculator in the y equals menu. So I'm skipping to example 3, and I did 2x cubed plus 5x squared minus 3x. I haven't graphed on this calculator yet today, so I'm just going to hit zoom 6 so that I'm back to a 10 by 10 viewing window. And I can see where one of the x-intercepts is. It's kind of hard to tell where the other x-intercepts are, right? So what you could do is you could actually go back to your function over here, and you could try factoring it without just using the graphing calculator. What factoring step should I do first to this polynomial? Divided by x. So using the greatest common factor, if I pull out x, what would I have left? 2x squared plus 5x minus 3. So those of you, I still have to give your test back today too. Some of us need practice on this factoring method. What would be the next step to factor this trinomial? Probably the box method, right? So in the box method, 2x squared goes in the top left, and negative 3 goes in the bottom right. And then I have to figure out how to put this 5x in the other two boxes. So I can use the diamond. I take 2 times negative 3, right? Negative 6 and 5. So which factors should I use? I need to multiply to get negative 6. Okay, so 6x and negative 1x. 6x goes in the box, negative 1x goes in the box. You write your factors now using the outside of the box. So 2x times x would give me 2x squared. 2x times 3 is 6x. X times negative 1 is negative 1x. And then I can double check 3 times negative 1 is negative 3. So if I wanted to factor this polynomial, it would factor into these 3 terms. X times 2x minus 1 times x plus 3. Who can tell me from these factors what the 3 roots have to be of this polynomial? Yep. 0, 1/2, and negative 3. So let's go back on our calculator now. Does it look like that's negative 3, that's 0, and that's 1/2? Right? So I can see what's happening on the graph. It's intersecting the x-axis at those points. And I'm going to show you a little bit on the next page about what multiplicity means, but this one it was good to remember that, hey, we could factor to find x-intercepts. Here's what the graph looks like. Here's a couple facts that are nice to know. How many roots can a polynomial function have? It can only have as many real roots as its degree. So a quadratic, x squared, can have as many as 2 real roots. What degree was this polynomial? It was cubic, right? How many x-intercepts did it have? 3. Cubic, 3 x-intercepts. Quadratic, 2 x-intercepts. Will every quadratic always have 2 x-intercepts though? No. I could have a quadratic that looks like this. Does that have any x-intercepts? No. I could have a cubic function that looks like this. How many x-intercepts does that have? 1. So it's saying it can only have as many roots as its degree. It doesn't say it has to have exactly that many. So it's a maximum number that it could have. The other kind of nice to know point is how many turning points can a function have? It can only have as many turning points as 1 less than its degree. So this graph that we just looked at, how many turning points did it have? 2, right? So a cubic function could have 2 turning points. This cubic function, how many turning points did it have? It had 0 turning points. Remember, a turning point is when it's going from like decreasing to increasing. So that's a turning point. This is increasing, 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 and increasing as it goes from left to right. So this had 0 turning points. So it's not saying that it has to have 2 turning points like this graph. It's at most 2 turning points. You don't really have to memorize that. You already know that a linear function, right? Linear has a degree of 1, right? So how many x-intercepts could it have? 1. How many turning points does it have? 0, right? It goes in a straight line. What about quadratic? It has a degree of 2. How many x-intercepts could it have? It could have 2. It might have fewer. How many turning points does a quadratic function have? 1. So the degree will always equal the maximum number. I should write maximum x-intercepts. And then this is the maximum turning points. Use the functions that you already know so you don't have to memorize something new. Here is something that is new, though. Multiplicity of a 0. So you're going to see this as your first unit in pre-calculus whenever you take it. So it's nice to have just seen it once before. Plant the seed. What is a multiplicity of a 0? It's the number of times that the factor appears in the polynomial function. And we're going to do a little roller coaster exploration after the fact, so you haven't seen this before. I want to go back to this example. How many times did each of these factors appear in this function? Once, right? X to the first, this is to the first power, this is to the first power. I have them each appearing 1 time. On the graph cut through the x-axis once at each of those x-intercepts. So there's something special that's going to happen. So zeros that have odd multiplicity cut through the x-axis. But zeros that have an even multiplicity bounce off the x-axis. So in this second example, I want us to graph this function. This function is the same function written twice. So x times x plus 4 squared times x minus 3. You can just look at my graph. Oh, it jumps up pretty high and pretty low. I'm just going to change my window real quick so you can see the whole function. So if I change my y min, y max. So here comes my graph. So it comes down to the x-axis, and then what happens? It bounces off, goes up to a turning point, and then it cuts through the x-axis, comes down here to a turning point, and then comes back up through the x-axis. So we're going to be able to start sketching this graph using our end behavior and our x-intercept multiplicity without using the graphing calculator. What are my x-intercepts? So I have 0, -4, and +3. Would you agree those are my x-intercepts? Which of the x-intercepts had odd multiplicity? So what that means is they only showed up once. X showed up once, and x minus 3 showed up once. So it has an odd multiplicity of 1. So this is new, so it's a little bit hard to understand at first. This x plus 4 factor, can't I write that as x plus 4 times x plus 4? It's considered to have an even multiplicity of 2. So what's happening at -4 on the graph? It's bouncing off the x-axis like a quadratic. So it's affecting that little section of the graph. It's making it bounce off the graph. And then it's cutting through at 0, and then it's cutting through at +3. So even multiplicity, it will bounce off the x-axis, and odd multiplicity, it will cut through the x-axis. So we're building on what we learned in quadratic world. We learned what a factor was and how to find the x-intercepts. Now we're learning in bigger functions how those x-intercepts behave. It's all connected. So let's do number 4 together. State all the zeros and their multiplicity. What is the first 0 for this factored function? X could be what? 0, right? So if you need to retake the test, even what we're doing right now should help practice what you already have been doing, that 0 is one of your x-intercepts, that positive 1 is one of your x-intercepts, that negative 2 is one of your x-intercepts, and then I get negative 2 again, right? It's the same in both of those. See how multiplicity is 2 for this one? Because it showed up twice. So these both have a multiplicity that's odd, and this has a multiplicity that's even. It's not because the number negative 2 is even itself. It's because it showed up twice, x plus 2 squared, right? The even is coming from the squared. So what would happen if I graphed this? It would cut through at 0, it would cut through at 1, and it would bounce off at negative 2. And so that's what's going to happen on our graph if we looked at this. 2x squared times x minus 1 times x plus 2 squared. I don't know how big this function is, but we know that our right side of the graph is going to go up because the leading coefficient was 2. What's the degree of this function? X squared, x cubed, x to the 4th, x to the 5th is odd, so the left side is pointing down. It bounced off at, oh, wait a second, isn't 0 even? Made a mistake on my own thing. Right, x squared right there. I missed that. So that x squared term is making it bounce off at 0. When I looked at the graph, I could see, oh, it's bouncing off at 0. I made a mistake. So it's bouncing off at 0, it's bouncing off at negative 2, and it's cutting through at x equals 1. Can you see that on my graph? So we're piecing, it's like a clue puzzle, right? You've got end behavior, x-intercepts, and multiplicity that are helping you put together a picture of what's going on. All right, so what you're going to do is you're going to go through these just like 3 examples. So you're going to think about the overall degree of the function. This is a key part for people because this is not in standard form. So if this was in standard form, why is this blurry? If I multiplied this all the way out, what would I get? 2x to the what power? X times x squared times x. Yeah, degree would be 4. Very good. So see how I multiply it all out in my head? This is a power of x, x squared, x. So that must be a total degree of 4. So it might have a maximum number of 4 x-intercepts. It might not have 4, but it could have 4. Its max number of turning points would be 3, right? It would only have 3 if it looks like this, like a W. So 1, 2, 3. It might just look like this and have 1 turning point. It might not have 3, but it could have 3. And find all x-intercepts and their multiplicity. So let's see, the first x-intercept is 0. What is its multiplicity? It has a multiplicity of 1, which is odd, right? So what is the effect on the graph? It's going to cut through the x-axis, right? Give me another x-intercept from this function. There's 2 more x-intercepts. Give me one of them. Negative 1. That's an x-intercept. What is its multiplicity? What's the exponent right there? Right? Its multiplicity is 2. 2 is even. So what's going to happen on the graph? It's going to bounce off the x-axis, right? And then how do I figure out the x-intercept from this factor, 2x minus 3? I set it equal to 0 and solve for x. So add 3 to the other side and divide by 2. So 3 halves, or 1.5. It also has a multiplicity of 1, which is odd, right? So it's going to cut through. So without looking at the graph on the calculator, your goal, we're going to practice this again Wednesday and again Thursday. I haven't even looked at this graph yet, but here's what I know about it, putting kind of together before you try the last 2. I know that the leading coefficient is positive. I know that the overall degree is even. So I know that the right end and the left end are both going to go up. I know that there's an x-intercept at 0, -1, and positive 3/2. And I know that at 1, it is going to, oh, sorry, let's see. I can't read all this. Oh, sorry, this is 3/2. It's odd, so it's going to cut through. So I'm going to come down and cut through the x-axis. Then I got to go back up and hit this one. So it says at 0, it's also odd. So it's going to go zoop, cut back through. At -1, it's even. So it's going to come down, bounce off, and then scoot back up towards that end behavior. It's going to look something like that W shape. So then you could use your calculator to verify how close you got. 2x times x plus 1 squared times 2x minus 3. So let's just see. I mean, it might be steeper than what I think it is, but at least I've got the general trend. So see how it comes, bounces off, scoots up, goes way down, and then cuts through. So I have the general shape. Sorry, something's weird that it's not letting you see that. But so I've got the general shape. That was pretty close guess based on not having a graphing calculator, right? So knowing the end behavior and the zeros. So you've got 5 minutes. I'd like you to try these last just 2 examples. When you get to the 3rd example on this page, you'll have to use your graphing calculator because we don't know how to do division yet. So you're going to have to find all your x-intercepts by hand on this one with the graphing calculator. So you want to finish those 2. And then your homework for tonight is 335. So you could actually get started on 335. It's really addition, subtraction, and multiplication. So for example, if you have to find the perimeter of these shapes, if you're adding up the sides, you're really adding together 3x squared minus 4x, 4x squared plus 5x, another 3x squared minus 4x, and another 4x squared plus 5x. So you have to add together these 4 different polynomials and come up with your perimeter in standard form. So you're looking for perimeter on 1, 2, and 3, so adding together the sides. You're looking for perimeter, and it's going to be they give you the width. You have to figure out which one's the length. On the back page, if it's area, you're multiplying the polynomials. Remember we did that yesterday with the box method. Length times width is the area of a rectangle. And then the last 4 are just writing in standard form, identifying the degree and the end behavior like what we did today. So you've got those 10 questions on 335 for homework. So you could do that during flex or leave it for home, but it's due tomorrow. And you're going to finish these 2 examples right now so that they're done for tomorrow. We'll start by checking our answers to that page first tomorrow.